a video where we're going to look at ways to model how ionic bonds form, and then really that results in an ionic compound. So we already covered like how our ions formed in the previous lesson. So today, I think, well, in general, we can talk about a compound. So compound is a result of something that is, two or more elements chemically bonded together. Not just mixed, but actually bonded. So there's something happening with their electrons. And today we're going to show and model what happens in ionic bonds. So ionic bonds are what make up ionic compounds. Are composed of ionic bonds. I know it sounds weird, but so for example, sodium chloride. So what happens with an ionic compound is the metal will lose electrons. So in this picture, and the resolution isn't great, but these are the sodium ions, and the chloride ions are negative, and there's going to be an attraction in all three dimensions. This is a crystal. So ionic compounds will have this crystal structure. So binary ionic compounds are just having a metal cation and a non-metal anion. So just really a metal and a non-metal. And you can see these are some common ones. We always talk about sodium chloride, but there's a whole bunch of other types of binary ionic compounds. If you remember the demo I did in class where I burned the magnesium, I was making the magnesium metal react with oxygen, and we had that white powder. That magnesium oxide, it could be used as an antacid or a laxative. In our toothpaste, we've got sodium fluoride. So it's the sodium ions and the fluoride ions that are kind of mixed into the other parts of the toothpaste. So there's different ways to model ionic compounds, and this is in your textbook. I'm going to be using these I'm going to show you, not all of them, but most of these. I'll just kind of work them through and show you. So first way of showing an ionic bond is with electron configuration. So if I were going to show like aluminum, which would be 1s2, 2s2, 2p6, I have to make sure I'm saying this right, looking at my periodic table, 3s2, 3p1. And then fluorine, 1s2, 2s2, 2p5, you can see that the aluminum is going to want to lose the 2 electrons in the S, the 3s, and that 1 electron in the p, because underneath that, then it will have a full octet of electrons, and it'll be like neon. So I'm going to need to get rid of all 3 electrons, and each fluorine wants to gain 1. So I do have to draw more fluorines. So then I'm going to pick a different color. So this p electron might go there. So now that fluorine is 1s2, 2s2, 2p6. This electron, one of the 2, is going to go to each of the other. So, and then the result to the right of the yield or makes arrow would be, we've got aluminum, which is +3, but in terms of electron configuration, it's really neon, because the electron configuration is just these right here. So similarly, the fluorines, or the fluoride ions, each become like a neon. And we would write that ion also. So, and we have 3 of those. So the electrons are being lost by the metal, and the metal becomes like the noble gas that precedes it, comes before it, which is neon. The nonmetals will gain until they have an octet. So they both, the aluminum and the fluorine, become like neon. And then the chemical formula, so you can see that we have 1 aluminum. So if we write the cation first, and then we have 3 fluorines, so we would put a 3 down here to show that that would be the correct chemical formula. Let me show you another way. So this is, we're going to show the orbital way. So let's draw an orbital diagram for sodium. So (3s1), and then oxygen. So that one right there is my sodium. Now I'm going to do oxygen. So you can see, I think this one shows it really obvious that oxygen is going to need 2 more electrons, and the sodium is going to give away 1. So we're actually going to need 2 sodiums to get everyone to have that octet of electrons. So let me draw that for you. So then if I were to show this, I would draw a circle and then show that electron going over there to that orbital, and this electron would go over there to that orbital. And they would be spinning opposite. I'm not going to worry about that. So then the result, the resulting, I'm not going to have you draw that, but it's really, the result is that you would have, sorry, I'm going to try to grab it. I'll just highlight it. You would end up with, you can see that sodium becomes like neon, and that the oxygen, so both of those are going to become like neon, and then the oxygen is also like neon. It's not always neon, it's just I'm giving you the smaller ones because I don't want you to have to draw orbital diagrams for really big ones. So the formula, if I put the cation first, it's going to be Na, and there's 2 of those for every 1 O. And we don't write the subscript of a 1. It's just implied. Okay, one more way to show an ionic bond is with electron dot diagrams. So if you draw the electron dot diagram for aluminum and for chlorine, and you can see hopefully that aluminum is going to lose 3 electrons, chlorine is going to gain 1. So one of these electrons can come over here, but it wants to get rid of the other 2. So I'm going to draw another 2 chlorines. So now I'm going to grab a different color. And that electron might go here. This electron is going to go here. So then what do we get once all that's done? We're going to get an aluminum ion. Oops, sorry. I don't know why. I'm going to put it in brackets, I guess, because that's what it becomes. And then we're going to get 3 of the chlorides, and they have all 8 electrons now. And they're -1. So the aluminum is +3 because it lost 3. And the chlorines are each -1 because they each gained 1 electron. And then our chemical formula is going to be AlCl3. So 1 aluminum and 3 chlorines. Now I want to talk to you about properties of ionic compounds. So I'm going to show you a PHET. And I'll also hopefully not lose you. So here's a PHET where we can add, salt to water. And we can look at this different ways. But I think I have to remember how to do this. I can put my conductivity meter in there, and you see it's showing the yellow lines. So it's showing that it's going to conduct electricity. it's not really, oh, the more I add, look, it gets bigger. The what's really going on though is if you the sodium ion, sorry, the crystal, watch me when I shake it. Wait, it won't let me shake anymore. Anyways, let me remove it and show you again. So when I first shake it out, that's the crystal where they're all attracted to each other. Once they're in the water, then they're able to move around freely. And that's why they're able to conduct electricity. And then when you look at water, I can throw in and you'll see the reason they dissolve in water is because water is polar. It has a positive part of water and a negative part of water. So if you watch closely, the sodiums are all surrounded by the red, which is the oxygen part of water, and the chlorides are surrounded by the white, which is the hydrogen side of water, which is partially positive. So back to, now we know why, when I do that, there are sodium and chloride ions that are dissolved in the water, and they're moving in between the electrodes, which gives us that conductivity. So back to the notes. So the ions in an ionic compound, when it's a solid, they're held really closely in place by all the dimensions of the crystal. And they're packed together in this repeating pattern, and it kind of balances out the forces of attraction and the repulsion. So they always go positive, negative, positive, so that not all the positives or the negatives are together. It's a very highly organized, thing, I guess, which we call a crystal lattice. So the crystal lattice is the crystal that's formed from those really strong attractions between the cations and the anions. And it's three-dimensional. So ionic compounds are typically soluble in water. So the water, remember I was telling you, it's gonna be partially negative on the oxygen side and partially positive on the hydrogen. So water has some charge, and so do the cations and anions. So they're soluble in water because of something we call like dissolves like. So if they're similar, they're gonna, dissolve in one another. Ionic compounds have very high melting and boiling points. So these are very large. And those are high because in order to melt, you'd have to break all of those attractions that are in the crystal. So water can do it with dissolving, which I always think is weird. That's pretty easily done. But yet if you have the solid and you try to melt it, like if you were going to put it on a hot plate or in a burner or in an oven, it won't melt. It'll be too high for you to achieve that temperature. Which shows us that the ionic compound bond is very strong. The crystals, just like if you think about salt, they're hard and rigid and brittle. So because of that, if they're not malleable, remember metals, you can pound them into shapes because we aren't going to get into the metallic bonding, but they're able to kind of slide by each other. But if you try to do that to an ionic compound, it's going to fracture. So they're very brittle and hard and rigid. And then they're called electrolytes. So what I was showing you with that FET just a second ago, they do conduct an electric current when they're dissolved in water. That's what an electrolyte is. And then the energy, if you remember, this is a picture of what we were doing with reacting the magnesium and the oxygen. Very exothermic. It's super high temperature. It's like 3,200 about Celsius degrees. That this, happens, and then it's very exothermic. So it took a little bit of energy from the burner to get it going, but overall there was more energy released than there was absorbed.